Hi, my name is George Dong, and this is my presentation on Lab 4, Circuits and Capacitors. The purpose of this lab is to predict the behaviors of circuits containing resistors in series, and examine the behavior of ohmic resistors and capacitors using the circuit construction kit. And some fundamental principles to understand this lab is the energy and current conservation and Kirchhoff's loop rule. And some equations we need to understand and make calculations in this lab are listed as follow. Here we have a simple circuit in which two 1.5 volt batteries are linked up to essentially create a larger 3 volt battery, and it's hooked up to two ammeters placed in series with two resistors, the top resistor being 47 ohms and the bottom resistor being 100 ohms. And the current through both ammeters read 0.02 amps because current is shared in all items in series. So this model exemplifies the loop rule because it takes voltage readings at various points of the voltage in between components where voltage drop would occur. So in the first picture, you have a voltage reading of 0 volts because it's the end of the loop and all the voltage should have dropped between all the components and reach 0 before reaching the EMF again. And in the second picture, we have a voltage reading of 2.04 volts. That is because 1.96 volts have dropped through the 47 ohm resistor, leaving 2.04 volts left. And the last picture, there's a voltage reading of 3 volts because the ammeter has no resistance technically, and therefore it is the original EMF that has been retained. And here we have a visualization of the voltage level as you interact with the various components of the circuit. So we start off with 0 volts and it climbs up to 3 volts from point A to B and stays there until point C because there is no voltage drop within the immediate wire until you reach that 47 ohm resistor. And that pattern continues all the way to the end. Essentially, the voltage doesn't change unless it's directly interacting with the resistor, which is why when it's at the wire, the voltage remains constant as well as the ammeter. In this example, an ammeter was hooked up parallel to the 100 ohm resistor, and this caused both ammeters to read an increased value of 0.06 amps compared to the original 0.02. This is due to the second ammeter producing a easier path for the electrons to follow. So essentially the 100 ohm resistor can be negated and the new loop used to determine the current for the ammeters would be the outermost perimeter of the circuit. In the example of the RC circuit, once the battery was connected, the bulb glowed as brightly as it could. This is because the capacitor is charging up, and while the capacitor is charging, it acts as a wire and transports current normally. However, as time goes by, the bulb gets dimmer and dimmer because the capacitor is reaching its fullest charge, and once that happens, it no longer can transport current. So for the timing for the 10 ohm resistor, the charge time was measured to be 9.51 seconds and discharge of 9.67 seconds. For the 20 ohm resistor, it was a charge time of 11.49 seconds and discharge time of 12.05 seconds. And here are the various voltage readings given at the different time intervals obtained by using a stopwatch and the pause feature in the circuit simulation kit. And on the right we have the graph of ln delta v over delta v naught versus t, and a linear regression line whose slope will come in handy later. This slope is actually equal to a theoretical negative reciprocal of the RC value. So if we take the negative reciprocal of the slope, which is 0.0486, we end up with negative 20.57. However, this is theoretically impossible, which most likely this is due to error in data collection, because it was kind of difficult to tell when the capacitor was fully charged and fully discharged. The expected value for RC was 0.2 farads times 30 ohms, which would give around 6 seconds. So my estimation was way off. So what if I recreated this lab in real life using actual ammeters instead of an ideal one? An actual ammeter uses real materials, and there is no material on Earth that can provide absolute zero resistance. So there will be resistance to be accounted for in the real ammeters. And because current is the ratio of voltage over resistance, the denominator of that resistance would increase, which would result in a smaller current, which this would lead into differences in accuracy. So completing this lab with real components such as a real battery and real capacitor would yield different results, because batteries themselves have resistance and they would wear down. Batteries wear down over time and can't provide as much voltage as they can when they are brand new. So repeated trials with the same batteries would yield different results, because you would start with a different delta V naught every single time.